All right, let's get started. So, last talk for the day. Um let's see how many of you I can keep awake until the end, right? Hope you all got caffeinated. All right, so brief introduction. So, my name is Vivekanand Gurumoorthy. I go by Vivek because sometimes in application forms I don't have enough boxes to fill in my name. But anyway, I'm from India. I did my bachelor's at College of Engineering, Indiana University, which is in the south of India. And then I did my master's at Texas A&M University at College Station. I specialized in analog and mixed signal design, which is what I'm working on currently. I currently lead a team in Marvel Technology in Santa Clara location. Uh, Me and my team, we basically work on high-speed SerDes design for both optical and backplane signaling, but majorly for optical. Um, and my expertise in specific, apart from analog and mixed signal, is optical high swing driver design. We will just briefly touch upon it, but not go too much into details of that. But if you're interested, definitely come to my talk in session 36 this year. So, professional fun activities. So apart, I've been an IEEE member for 10 plus years. I've had multiple publications in ISSCC. Outside of work, I'm an amateur speed and adrenaline enthusiast. If you are a circuit designer, you need to be an adrenaline enthusiast. But if you try to do stuff outside of work, which increases the adrenaline, probably your stress level at work will be lower. But we can talk about it later. And I'm also a coffee aficionado, so if you have any questions about coffees from which part of the world and how to make them, different types, again, come talk to me. All these questions are welcome in the last 10 minutes, except for circuit design, okay? All right, so a brief introduction about what we do here at Marvel. So, Marvel is a multi-billion-dollar company, but the business group that I work for is called the PAM4 ODSP group. ODSP, it stands for Optical Digital Signal Processing. Actually, maybe the timer is not on, just to make sure I don't go over. Yeah. Okay. So as I was saying, we do PAM4 DSP. So I'm glad Kevin gave an excellent introduction of higher order modulation. So now I can just say PAM4 because you all understand what PAM4 means. So we basically design chips that go into these data centers. We'll briefly touch upon where these things go in and how it's being used. So basically, we design chips for front-end and back-end networks, which are communicating at up to 1.6 terabit per second, all the way down to 100 gigabits per second. So it's not in a single lane, but single lane can go somewhere from 50 gig to 200 gigabits per second. And we'll see how we do that, right? The screenshots above, these are some of our latest products that increased our adrenaline, as I've talked about in the last slide. So the first one was a 1.6 terabit per second chip. We did one chip in which there were 4 lanes, and each lane was transmitting at 200 gigabits per second. You package 2 of them, you get 1.6 terabits per second. We have also done solutions where we do 50 gigabits per second, but a lot of custom integration that goes into it that a lot of these cloud customers like. So cloud, data center, all these keywords, I'll touch upon what these mean and how we fit into this, right? The team I'm working for, like I said, multiple products with, a lot of innovation awards as well. So if you're interested, go to the Marvel website, go into the PAM4 DSP links, and you will see a lot more details. Okay, that's the last of the marketing slide, I promise. More engineering, moving on. So this is outline for the talk. So we'll first look at the motivation for optical communication. And obviously, I'm going to talk about AI because that is the keyword if I have to increase my stock value right now. So we'll talk about what AI data center interconnect infrastructure looks like and why or how optical communication circuits fit into that. And then I'm going to give a brief introduction of silicon photonics. Then we'll look at how to design circuits for this. We'll design together a simple transmitter path circuitry, look at what that looks like at the output, and then we will design a simple receiver circuitry and measure those results. Okay, So moving on to the main motivation slide. Like I said, AI data center infrastructure. So what does this mean, right? So say for example, you go open your most favorite social media app, or one of your most favorite email app, right? You go, like click on a button and request for information. That information is sitting somewhere in a data center, maybe in Las Vegas or somewhere far away. So, but at the click of the button, you get the data back. And how is that happening, right? So, that request is being sent through the internet, and the internet is connected to the data center through multiple levels, which is what is shown in this diagram on the left: transport, core switch, edge switch, and like TOR switch. TOR means top of the rack. Top of the rack switch is basically the one in this data center on the top here. So all we are doing is trying to figure out how fast we can get the data out of those servers and send it back to you, right? So this is where optical communication comes into picture. So almost all of these switches, all the way from the TOR switch to the transport level, are all connected through optical modules. So we look into what is there in these optical modules, right? And we will also see why it is super fast. Now, there's one more, right? Like I said, I'm going to keep using this word AI multiple times for stock value. So like say for example, now you go also use your favorite AI app. There are multiple ones, I'm not going to name names, but you go put a search query into it. It's doing a bunch of backend processing to do the inference based on all their LLM models, and you need to get the data out as fast as possible to you guys, right? So that is where this AI switch comes into picture. So this hierarchy is entirely similar to what I showed in the last diagram, but once the AI inference all happens, that is where the optical modules come in to get this data out to you as fast as possible. So some of these pluggables in between here are working at like data rates of 112 gigabits per second. Now we are moving on to the next generation, which is like 224 gigabits per second. So we'll see how we are like designing circuits to get to those data rates. So the optic side of things, which is basically the laser side, is also scaling equivalently for these speeds. And a lot of these connections are up to like 500-meter reach internally, but when you get it out to the internet servers, they also can go up to 20 kilometers, which is where optics are in much more favor, right? All right, so why optical communication? This can be explained with a very simple plot here, right? So this plot basically shows the signal loss versus distance. And this is compared for three different things. One is a Cat6a copper, which is like electrical signaling, and then a multi-mode fiber versus a single mode fiber. So a single mode fiber, what it means is you just send one amplitude, one lambda light through that fiber, while in a multi-mode fiber, you can send multiple lambdas. Like imagine them being of different frequencies. It's not really a frequency, but of like different frequencies that can be sent through the same fiber, right? You can clearly see that if you use like a single mode fiber, you can go up to 20 kilometers with like minimal signal loss. With multi-mode fiber, you may improve the throughput, but obviously the signal loss is going to be a little worse even with shorter distances. And in Cat6a copper cables, you can go ultra high speed in like short distances, but beyond that, the signal loss is going to increase a lot, right? So the main advantage of using optical communication is that you can go longer distance with higher speeds and higher bandwidth, and it's also pretty cost effective, right? Like once you lay down all your optical fibers, it will last forever, and these are also immune to a lot of interference. Now, I promised you guys what these pluggable modules look like. I was going to show that, right? So here is a picture of what these pluggable modules look like. So on this left side here is this optical DSP. The optical DSP is what my team does. So this is where the circuits for optical communications comes into picture, right? But you have a bunch of digital data, you take it and convert it into analog, and then you need to use the data to drive a laser that is going to send light through a fiber. So that is just light through the fiber, right? So from the optical DSP, we process the data, send out an analog signal which goes into an external circuit called a driver, which are usually non-CMOS conventionally, and that drives a laser. Laser, I'm pretty sure you guys know what a laser does, right? I mean, it's just a light that you're trying to modulate. And that drives it through a fiber, and on the other side, when you like receive the light back, it goes through a PD. A PD is a photodiode. So you have it in light form, and like what do you need to do? You need to like convert that light into either a current or an voltage to post-process it. So the photodiode basically, it like detects the light and converts it into a current, which then is converted into an voltage by a TIA. TIA is, it stands for transimpedance amplifier. It's a current to voltage converter. Now, we have transmitted in light, we have recovered the light back and converted it back to voltage. We can take that into our DSP and we can do a bunch of stuff to like post-process it to achieve the speeds that we want, right? So there may be a couple of terms that I might use. For example, in the lasers, there are a couple of types of lasers called EML laser. So it's basically an electro-absorption modulated laser, or a SiPho, which is a silicon photonics laser. One example of a silicon photonics laser is a Mach-Zehnder modulator. We don't need to go into the details of each one of them, but just some like terminology to know what these types of lasers could be. Right? Now, let's go into a brief introduction of the Mach-Zehnder modulator alone. Fair warning, I'm not an optics guy, I'm a circuits guy, but I'm going to give you an introduction so you know what kind of circuits we drive in order to make this light-based transmission happen, right? So this Mach-Zehnder modulator can be, can be like manufactured in different process technologies. The details of which we will not go into, but at a modeling level, what it looks like is you have a light coming in from the input side, which is being split using a multi-mode inference coupler, which is what the MMI stands for. So it's split into two parts, right? And then it's sent through a traveling wave electrode. So the label where you see P and phase shifters, those are traveling wave electrodes. So you take the light, split it, and send it through the traveling wave electrodes, and you drive those traveling wave electrodes with an electrical signal, which is where all the circuitry that we are going to talk about comes into picture, right? So you apply an electrical field across the traveling wave electrode when the light is passing through it, which will basically change the index of refraction of the light, or you can also change the speed of the light, right? So basically you will have constructive or like destructive interference in the two parts. Those are then combined together and then transmitted out. So essentially you're taking the light, you're modulating it with the data that you want to be transmitted, and you're sending it out. And that transmission is happening through a fiber. And all the circuitry that we're going to talk about is basically how we drive this, right? So if you look at the bottom right diagram, this part is the traveling electrode and the actual MZM model I was just talking about. And this is just a simple example where we have a chip driving with an open drain driver into those traveling wave electrodes. And when you do that, you get an optical eye like this. This could be an NRZ eye, PAM4 eye, or whatever modulation technology you want to use, right? And the plot here on the left is basically a plot of the output characteristics of this MZM. We call this the B pipe plot. It just shows how, when you apply an electric field, the optical power is getting modulated, and how the optical field is being generated. Let's not go too much into the details of this, but this plot is just to show what the characteristics might look like. So we have established what we are going to drive. We take a laser, we are going to modulate it and send it. And why is it happening? And we already understand why it's so fast. Now let's go figure out how to design these circuitries to make this high-speed transmission possible, right? Oh, and before that, like I promised, we will, there are like different ways to do this, right? So if you take a look at the module that I talked about earlier, I had a driver circuitry here, which is external, right? But there are ways where this driver circuitry can be absorbed into the CMOS section, into our DSP, and that has a lot of advantages, right? So if I go tell someone in the, who's like manufacturing this module, hey, you don't have to put one more extra component. I'll provide that as part of my own chip. They're going to love it because it's like smaller form factor. They don't have to account for that in their PCB, lower power, lower cost for them, all that. So there are only a few companies that can do this. Ours is one of them. We will not delve too much into the details of this, but definitely, if you're interested, come to my paper in session 36 on Wednesday. All right, now let's take a look at some of the architectures. So first, we will take a look at the overall architecture from like a very top-level block diagram, right? So we are transmitting data, we are receiving it. So what are we doing in between, right? So the data usually is in the form of zeros and ones, as you all know. It's in like digital, so it's easier to it's easier to pre-process it with a bunch of digital signal processing. Now you need to take that data and convert it into analog, which is where a DAC comes into picture. It's a digital to analog converter, and that DAC has to be sampled using a clock signal. So this is where some of the details that Kevin gave in his talk was very helpful, right? So think about the single bit response that he was talking about. That applies everywhere, not just in like wireline, right? Even in optics, a single bit response is pretty important, and you need to have a clock reference in order to convert that DAC into the digital into an analog voltage. And then we drive that out to the laser. Now we are like modulating the laser. It goes through the optical fiber, like however long you want to send it based on different types of lasers. You take that, convert that light back into a current, and then you receive it in a front-end front-end receiver signal path. Basically, this AFE means an analog front-end, right? So you take that signal and precondition it in analog, and then you convert that from analog to digital, which is where, again, you need to have a PLL, which is a clocking source, plus a CDR, the clock data recovery, which tells us where to put the sampling point. You convert that into digital zeros or ones, and you take it back into like post-processing it in the like DSP. So this is the overall architecture of what an optical transceiver will look like. Now let's focus a little bit more on the TX side of things, right? So TX is the transmit path. Now I want to start transmitting this data out, right? And this is an example for 100 gigabits per second per lane, like architecture. So here what you have is the DSP sending your data in zeros and ones, right? You have, the DSP cannot run at the same rate as what you want to transmit here outside. Like if you want 100 gigabits per second, your DSP is not going to run at the same rate. It's going to run at a much slower rate, but it will send me a bunch of data in parallel, right? You have a bunch of data in parallel which you need to serialize in order to make them fast enough. So that is where the serializer comes into picture. So in this particular scenario, we have data coming in at 64 UI. So again, if I refer back to Kevin's talk, you know the baud rate and UI is 1 over baud rate, right? So you have data coming in at 64 UI rate, which is much slower, and we serialize it, right? The 64 UI is coming in parallel. We serialize it into up to a 2 UI in multiple stages, and then you take the 2 UI and serialize it one more time into a 1 UI stage. So to do all this, you need a clock path, which is where this box where you see the clock domain comes into picture. We'll talk about why it needs to be a specific clock rate in the subsequent slides. But imagine you get a clock, you do a bunch of correction, and you use that to convert the parallel data into serial data. And once you get it to the 1 UI stage, which is the highest speed, you have to transmit it out, right? So that is where the DAC comes into picture. In this case, we are showing a 7-bit DAC. So if we say a 7-bit DAC, you basically have like 127 levels, right? 2 power 7 minus 1. So why a DAC-based architecture? So to answer that, we need to go back to some of the equalization techniques that we saw in the wireline talk, right? We talked about FIR, FFE. A lot of those things, when you do it in the digital domain, it's much, much easier, right? So all you're doing is you're transmitting a 7-bit DAC output, which is 0 to like 127 levels, right? And you can modulate that however way you want in the digital. So that is why a DAC-based architecture is very, very helpful. And also, we have a lot of other techniques in there where we also compensate for like nonlinearity, distortion, and once you have a bunch of bits in like zeros and ones, it's so easy to like manipulate all of them. So this is the overall architecture level diagram of how to transmit the data out. Right? Now let's take a look at a couple of these sub-blocks. So first, let's take a look at the TX serializer. As I was saying, like all the like digital zeros and ones, they cannot work at the same rate as the rate you want them to. You want our TX to be like transmitting, right? So obviously it's going to work at a slower rate, but in parallel, which you're going to serialize. So here, in these two diagrams, I'm going to give you the answer, right? So the output is going to be at the rate that you want to transmit. Well, we are all engineers, so we can backtrack what is really happening here. So say, for example, you need to transmit at 56 gigabits per second. So 56 gigabits, when you do a PAM4 transmission, it's 2 bits per symbol, right? So then the baud rate is basically 28 gigabaud, which means the Nyquist rate is half of that, which is about 14 gigahertz. So let's say you get a 14 gigahertz clock here. And let's say you have two sets of data in parallel here, which are at 28 gigabits per second, right? And this is just a simple flip-flop and latch-based circuitry, right? So just follow my, my like green arrow. So on the like rising edge of the clock here, the data from this DO2 is going to get sampled, and it's going to wait here at the input of this mux 0, right? And then once the clock goes to its low level, that data is going to be transmitted out. But that data is going to be on only for this time period, which is basically one UI, right? And at the same time, on the other side, this D13 data is getting sampled by the same rising edge, but it doesn't get to the mux input because there is a latch in between. That latch in its low state is when it's going to pass the data through, right? Until it's going to hold the data here. And on the next rising edge, you get this D13 getting passed out. So essentially what you are doing is you have data running at half the rate here in parallel, and you are taking that and serializing it into full rate here. So this is just a simple 2-to-1 serializer, right? Now you can extend this theory all the way back. Like whatever rate the zeros and ones need to run at in the DSP, let's say it's like a data rate over 64, just keep going back how many other ways you want to like make it parallel. So that's all a serializer does, right? So the serializer takes that parallel data and serializes it back to give us the full rate data. So now that we have done that, how do we transmit this out? So to transmit it out, let's take a look at what the DAC architecture needs to look like. So we talked about a 7-bit DAC, right? 7-bit DAC is basically 127 levels. Let's talk about how to design each unit DAC. So to design these each unit DACs, you can go 2 ways, right? You can either take an voltage and try to send it out through a bunch of inverters with the 50 ohms at its output. Now, why 50 ohms? So I think there were a couple of questions in the earlier sessions as well. Like almost all transmission lines are 50 ohms matched. So you want to match to the external transmission line so you don't have any type of like reflections and all those effects. So let's assume that 50 ohms is a universal given impedance that you want to match to. So that's the reason for the 50 ohms. So this is one way to do it. And like what is the other way, right? So the other way is you take a current and you're going to switch it between the two sides onto a 50 ohm impedance which we call as the like back termination. So for a given swing and a given supply voltage, if you do the math and look at the power comparison between these two, the SSD-based DAC, which is what is also called an voltage mode DAC, that has almost 1/4 the power of a CML DAC, which is also called a current mode logic DAC, right? So obviously, in terms of power consumption, this looks like pretty small, but is there any other advantages to it? And obviously, yes, right? So it's just an inverter-based DAC, so it's extremely like linear. You're switching from 0 to 1 level all the time. So this has pretty low distortion, but it has some other disadvantages like bandwidth limitations, which we will go through soon. The current mode logic DAC, it's slightly higher power, but the linearity is not as good because as soon as you have a current source here, as you all know, you need to keep the current source in saturation. So if you need to keep the current source in saturation, you are like limited to how much voltage you can swing by and how that affects the linearity of this current source itself. However, there are like reasons to go for this DAC because the bandwidth of these DACs are much higher since you are moving in current domain. So before we design more into the CML side, let's just look at why an SST DAC is not that advantageous, right? So in the SST DAC, like I said, it's just an inverter with a 50 ohm resistor at the output. Now, like what are the problems that could happen here? So I'm trying to transmit data out at 56 gigabits per second. Now, the input here is switching at like similar rate if it is at 1 UI, right? So when it's rising or falling, there could be instances where the PMOS and NMOS are going to be turned on at the same time for a brief period of time. And that's going to have a lot of current sink between VDD to VSS. And you never want that in any kind of chip, right? Because if this happens at high scale, the amount of power consumption that goes on through the chip is insanely high. So you always want to limit that. So how do we limit that? So one way to do that is here. So instead of putting the 50 ohms in series here, you take that and add it along with the PMOS and NMOS. So this will be 50 ohms and this will be 50 ohms. Now, when you're transmitting it out, only the NMOS or the PMOS are going to be on at a time. So the output is still going to see only 50 ohms, right? But there are other disadvantages to it. So this comes with its own set of additional parasitics, as I've shown here. And this is going to limit the bandwidth, right? And also, the other thing to note here is you can also do like a break before make circuitry. So both PMOS and NMOS are going to be on at the same time, like only if you drive with a single signal, right? So what if you break them between the PMOS and NMOS and introduce an offset between them a little bit somehow? That could help, but that has its own design complexity as well. And overall, if you do all this, the bandwidth of these devices, these kind of DACs are going to be pretty limited. So then what do we do? So let's take a look at the CML architecture, right? The CML architecture, like we said, is going to be fast because it's just switching currents between the two sides. But we had linearity issues with this particular architecture because the current source needs to be kept in saturation, and then there could be matching requirements between the different DAC units. So how do we solve all that? So to do that, we have this other architecture called a pseudo CML, right? Just simple two transistor design. The top transistor is basically the current source, and the bottom transistor is the switch, which is turning on or off. So like Human was saying, we try to keep the circuits as simple as possible, right? The faster you want to go, the simpler the circuits need to get. So, just a simple two transistor design at the output DAC. So when you do this, now this switch acts like a source degeneration in a sense for these transistors. And you don't have any headroom requirement because you're going to swing full voltage range here at the input, and the voltage drop across these transistors is going to be pretty minimal. So you solve the headroom issue, the linearity gets better, and we have the same like bandwidth advantages with the pseudo CML architecture as well, right? So now we know what kind of unit DAC to use, and a little bit more about the equations, right? So I'm not going to go into the exact equations, but if you want to drive a particular swing, let's say like 0.9 volt peak-to-peak differential swing with a supply voltage of 1.5 volt, you can just do a simple, current calculation to figure out how much current you need to switch between the two sides. And if you want a unit DAC for a 7-bit DAC, it's just that total current divided by 127 units. And you will get the current that you need to design for this DAC. So in this example, it's 142 microamps. So you just take a simple two transistor design the DAC, and now you need to build 127 elements of this, right? Because it's a 7-bit DAC. And one other thing I would also like to touch upon here is, even though we solved a lot of issues in the pseudo CML DAC, it can still have headroom issues across PVT, right? Like you go to a slow corner or lower voltage, higher temperature. There could still be, headroom issues. So one simple technique that is used in the industry prevalently is to do like a PMOS bleeder. We call this a bleeder because all this does is it just keeps bleeding current onto this node. So essentially, you're dumping more current into this node in such a way that the like voltage here keeps increasing. Right? Simple KVL loss. So you just so this part of the circuit is sinking current, and you are like sinking current on this path in order to increase that voltage, which basically increases the common mode and hence the headroom. So we have essentially solved almost all the issues that we had in this DAC design, right? Now we have the unit DAC. We go on and construct the full 127 units, right? So all I've shown here is the 7 bits. We usually convert the top to MSB from like binary to thermometer, because I think Professor Ali might have touched over some of the DAC theory earlier in his lecture, where when you go to the MSB section of things, the switching will have like a bigger value, right? So especially when you do that in the actual implementation, there could be a lot of mismatches and glitches which you want to minimize. So basically, we convert them into a thermometer encoding, and we take the current. We like sum up the currents and like dump it onto a back termination of 50 of like 50 ohms. So this is basically the impedance matching. So if you look at it from this node, you have 50 ohms on the top, and ideally, the output impedance looking through here should be infinite, right? So then your essential, your output impedance looking through the output node is 50 in parallel with the infinite impedance, so it's going to be 50. That's the ideal design. And in between, you can also use bandwidth boosting techniques like this, which is basically a T-coil. A T-coil is just a couple of inductors with mutual coupling between them. So, all it does is it kind of resonates out the parasitic cap to make sure that the bandwidth doesn't take a hit. All right, so we did this, and this was a few years back, and we were able to like measure a 56 gigabits per second data output with a swing of about 710 millivolts. So this is where the different levels come into picture, right? So this is PAM4. So this is the -3, -1, +1, +3. And the way to visualize it is, let's say this is like 710 millivolts, right? And you have like 127 bits. So, like 127 like levels out of the 7-bit DAC. So if you just equally space them apart, so if this is 0 volts, that's level 0, and then you take the equally spaced bit level, which will be 127 over 3, which is 42, right? And that will be the 1/3 voltage here, plus another 42 is this voltage, and plus another 42 point something is this voltage. So that's all there is in this PAM4 transmission. We also did the same thing with 112 gigabits per second PAM4. In this case, we were able to get a swing of 610 millivolts. Higher the data transmission speed, more loss, like we saw in the earlier presentations, right? So obviously, you're going to lose more swing. You try to compensate for some of the ISI loss by using FFE, and you will lose a little bit more swing because of that. Now, we pushed the limits to 100 gigabits per second, right? Can we go even higher? So let's try to do 200 gigabits per second. So just imagine the magnitude of what we are doing here, right? So if you get a fiber optic internet line to your home, it's like maximum you get like 1 gigabits per second, right? So this is like 200 times of that, and it's in single lane, right? So when you try to do that, the circuit design part of it gets a lot more complex, right? So we talked about the baud rate and the clock rate for 56 gigabits per second transmission. We established that the clock rate was 14 there, right? Now we are trying to quadruple the data rate, but can we really quadruple the clock rate? So 14 times 4 will be 56 gigahertz. Trying to transmit 56 gigahertz inside a CMOS circuit is going to be next to impossible, right? So like what do we do then? So we keep the clock rate low, but then we make the data more parallel. So that's why we have like a 4-to-1 DAC. In the previous case, we had the last stage to be a 2-to-1. So here it will still be a 28 gigahertz clock coming in, but instead of instead of serializing from 2 stages, we serialize from like 4 stages. And the serializer section, the concept remains the same, right? But once you have more stages to serialize from, you run into a lot more non-linearities, right? So you have a 4-phase clock here. how is the skew between them being compensated for, how do we calibrate that out. So all of that requires additional circuitry. So we have a Cal ADC, we have a low speed PI for data alignment and stuff like that. So let's just briefly take a look at what this design could look like, right? So for the 200 gig design, you have the same 7-bit DAC or a similar 7-bit DAC. The current output of that is summed up, and then you convert that into an voltage. So what you can do here is, if you try to do it in a single stage, you're going to have a lot of parasitic cap here in this node, and it's not going to be easy to meet the same bandwidth requirements as before, right? So the approach we take is, we try to keep the bandwidth at each of these intermediate nodes high enough, but then split up the workload between 3 different stages. So you have the 4-to-1 DAC, the current is summed up and converted into an voltage. Now that voltage needs to be driven out. So we could have directly gone from a DAC to a driver, but when you go at these speeds, there's a lot of parasitic cap in between. Remember the CGD cap that Human was referring to? That plays a major factor in our designs as well at the speeds. So there will be a lot of kickback that goes onto the like DAC stage. So in order to prevent those kickbacks, we introduce an in-between stage, which is a pre-driver. So this one might be familiar to a lot of you, right? I mean, I think Professor Ali talked about the flipped voltage follower. So this is essentially a flipped voltage follower. So if you look at it from the input here to the output, it's a simple source follower. So the output impedance looking here should be ideally 0 or very, very minimal. And we have this feedback node in order to make this flipped voltage follower as fast as possible. So if there is any kind of kickback coming from the output side, the low impedance of the source follower kind of absorbs it. It doesn't let it go back to the DAC stage and hurt its performance. So we have this pre-driver stage, and then it goes to an output stage. The output stage, if you just simplify this and eliminate this transistor, it's just like an inverter, right? Like I keep saying, the higher speeds you go, simpler the circuits get, right? So this is like we call this a push-pull stage with a NMOS input, and also it's AC coupled to a PMOS input. And we have a cascode device in between, because when you start swinging full swings here, you need to make sure that the devices don't go out of their limits. Essentially, whichever fab you manufacture it with, they will tell you, okay, you can't take this transistor beyond a particular limit of voltage swing, right? So we use a cascode device to protect those. And then we have the same 50 ohm termination with some bandwidth boosting techniques. So we did all this. Oh, actually, I'm going to skip this slide in the interest of time, but like definitely go through the details of this. This is pretty simple. All we are trying to show here is what is going on inside this DAC unit cell, and how we convert the like 4 UI data into a 1 UI data. And if you just follow this timing diagram along with the circuitry here, it will be pretty easy to figure out what's going on here. So we did this, and we were able to get a 212 gigabits per second PAM4i. So now you see we got up to a 800 millivolt swing with a bandwidth of greater than 55 gigahertz, and having open eyes, like 3 open eyes where the signal to noise and distortion ratio is going to be pretty good. It's a pretty massive achievement in order to get up to 212 gigabits per second. Okay, so we will briefly touch upon receiver. So we talked a lot about the transmitter. We as humans like to talk a lot, but listening is very important. So if anyone is sleeping, wake up. We are going to talk about the receiver side of things, right? So we have sent the light. We have converted the light from the like light domain into a current, and then there is a TIA which converts it into an voltage, and then we do a bunch of post-processing here, right? So one of the things that is easy for us in analog, especially on the optical side of things, is we don't have to deal with a lot of analog equalization that Kevin was talking about. The channel between the TIA to our DSP is pretty small. We don't incur a lot of losses. The main thing that we deal with is the noise inside the TIA. So we don't have a CTLE, we don't have any major circuitry in there. We keep it simple, but we need to have them as high bandwidth as possible, right? And then you precondition the signal, and you have a time interleaved ADC here. So time interleaved ADCs are a concept that we can go into a separate lecture on, maybe a topic for next year's like Circuit Insights. I'm not going to touch upon that too much. But imagine going from a serial data to a parallel data, right? In the TX, we went from parallel data to a serial data to make it fast. Now you have a fast 1UI data, you need to go from serial to parallel data, which is slower, which is what the entire time interleaved ADC does. A simple circuitry that we had in 200 gig to do this, basically the input termination for obvious signal integrity reasons. We take that signal, and if you ignore all the inductors here, you will see that this is just a simple common source amplifier, right? An NMOS with like a source degeneration, and we have a capacitor degeneration here. We did say we are not going to do a CTLE, like what Kevin was talking about, but we do need some amount of bandwidth boost in order to transmit, like post-process data up to 200 gigabits per second, right? So we have that, and all these inductors are just bandwidth boosting techniques, right? And you take that and send it through a VGA, which is a variable gain amplifier, because the input swing can be of different levels, right? You need to be able to change the gain of the voltage that is going into the to the like ADC section. So again, if you simplify this, this is also like a common source amplifier, but in the PMOS domain with a source degeneration, which is going to change the gain. This is not capacitive, but this is more resistive in like lower frequencies. So that's all there is to a simple RX AFE, right? Now let's all put this together. Now, if we do all this, right? So this is an example. Example measurement with one of our 100 gigabits per second optical SerDes. So we had a 53 gigabaud PAM4 being transmitted out from our TX, and we tried to look at the eye diagram at the output of the laser, basically. So you can see the laser output is measured in terms of microwatts, and you can see we get 3 PAM4 eyes, and now that is transmitted through a fiber, and it goes through a photodiode, and we measured the eye at the TIA input. You can see it's pretty noisy, right? This is happening at 100 gigabits per second. But you take that and do all your magic inside the DSP chip, and you will recover the 4 levels that you need. Essentially, these 4 histograms are the 4 levels in your PAM4 eye, right? Like -3, -1, +1, +3. As long as you're able to distinguish between the 4 levels, you have recovered most of the eye. And along with this comes all the bit error rates, the digital communication theories like the forward error correction and all the other stuff which makes this possible. All right, so that concludes my talk. So almost all the circuitries that we designed today, they form the backbone for the interconnected world, right? Like you go stream a video, do things on your AI, everything is going through some kind of optical modules like this. And the need for going faster is only increasing, right? So it's going to be a pretty exciting field. So I really encourage all of you to delve more into it. Feel free to stop by to ask more questions about this. I'll be happy to answer. Thank you.